He worked on the NASA Lunar excavator. I met Sam at the tech shop. The tech shop is a great place to go to meet people. Okay, and he's telling me he's working on this robot, and I'm seeing him take a big chunk of aluminum, and he says he's making wheels. And I'm going like, why would you take a big chunk of aluminum and make a wheel? Why don't you just buy a wheel? Of course, I didn't understand he had weight constraints, so that's why he was making aluminum wheels out of big chunks of aluminum, making them smaller. So I'll let Sam take over and explain the rest of his robot.
I'm going to need to move things around.
You need me to operate the laptop.
Tell you what, we'll move if it comes down.
I thought it was just a robot that would dig its way through.
Did you?
Oh, it has a train circuit.
Actually, people are talking about this. You can go stand in front of me.
All right, yeah.
Yeah.
Or something like that.
Okay, let's get started.
So, like Wayne just said, I'm Sam Waldbaum. I built these two robots. This one was for the 2008 NASA Regolith Excavation Challenge. This was for the 2009 challenge. And I'm gonna try to run through this stuff real quick because I got a lot of slides. All right, so quick overview. I'll explain, what the Centennial challenges are and what this one was for, and then I'll dive into each one.
Do you mind using the mic?
Yes.
That works.
Get that next one.
I don't know enough about
Can you hear me?
Yeah.
Just
Just say, tell me.
okay.
Just say next.
Okay, so the NASA Centennial challenges started, I don't know, 2003. Matt could probably say better. I don't know.
Yeah.
There's a bunch of them. I didn't know about them until 2008, and I heard about the Regolith Excavation Challenge. And I looked at it, and it looked like something I could do. So I decided to do it. And there's a lot of money to be won, which is a big motivator. So I signed up. That was really it. And so I heard of, the 2008 competition was in August, and I heard about it in May or April, and didn't have much time to really prepare. Next slide, please. Okay, so why does NASA even care about regolith? It has a lot of oxygen in it, and they want to go to the moon. They need air for people. I don't know. They might need air for something else too, growing plants or something. Helium-3 I've heard about. They'd be interested in for energy research and maybe some other materials that they would find. Yes. Next slide. Okay, so regolith is really weird stuff to work with. Regolith is the topsoil layer above rock. That's I think the definition of it. It's basically just dirt, and it's really weird on the moon because there's no erosion. It's been bombarded by micrometeorites for a long time, which causes agglutination, which makes this really jagged, interlocking, kind of Velcro, flour, fine soil kind of stuff. So it's really grainy. Actually, if one of you wants to open this up and pass it around, you can take a look at it. That's
moon soil?
That's not moon soil. That is the simulant. if that was moon soil.
Please do not spill it.
Yeah. So you can just try to just jam your finger in and see how impenetrable it is. It's really where it's stuck. Yeah, so it's really has a lot of static cling. It sticks to everything. It gets into motors, gets into gears, it jams everything up. So it's a big challenge to work with it. Next slide, please.
Wow.
Okay, so that's why NASA wants to have the competition. Here's what the competition is about. For in 2008, which is this robot, which is mangled, it's been cannibalized and broken and bounced around in cars for 2 years, so it's not in good shape. It will not be doing an active demo tonight. Okay, so the goal was to fully autonomously excavate a minimum of 150 kilograms of that lunar regolith simulant in 30 minutes. In 30 minutes, yeah. Is there anything else? That's basically the main goals. And this was going to be done in a 12-foot by 12-foot sandbox. There were going to be 4 randomly placed rocks. The robot would be randomly placed in a random orientation. So when it came up, it had to figure out where it was. It had to get the minimum 150 kilograms of dirt from anywhere in the sandbox, drive up the ramp, and dump it into a collector. And the only way it had to navigate is a beacon or a marker or something that you could put on the ramp. And that was subjected to certain limitations too. Next slide, please. Okay, so the restrictions were 150 watts max power, which was provided through an umbilical by the organization that was running the competition. It had to be under 70 kilograms, which is 150 or 160 pounds, something like that. It wasn't stated, but there was through other rules, it was kind of implied that there was a maximum size for this thing. And again, there were unknown rock positions and unknown starting position for the robot. Some other kind of loophole closing restrictions were you can't have explosives, you can't anchor this thing into the ground, you can't bury it, you can't use vacuums because on the moon there's no oxygen, there's no atmosphere, so you can't vacuum or you can't use incompatible processes like sonar or fans or helicopter blades or anything. Next slide. Okay, so knowing the requirements, the trade space for coming up with this design is choosing somewhere between a little remote control backhoe and a ridiculously large and huge and bucket wheel excavator, the biggest excavating machine I could possibly see. So coming up with a design was moving around the trade space where everything interlocks and you go back and forth in the trade space a lot as an iterative process, but it was primarily driven by the navigation method. And that was because of the autonomy requirement, which really was the main challenge, even though I think NASA, they were interested in the digging, but we got stuck on the navigation part. So because of the navigation, complexity of the navigation, that drove many of the other requirements. Next slide. Okay, so my starting point, let's see, 4-wheel drive, skid steering. I was going to use the camera to actually do the navigation so it could figure out where it was in the sandbox and locate the ramp. When the marker I was going to use would just be a board with 2 different colors on it so the camera could identify its orientation based on the relative position to those colors. I'll explain that more later. The weight ended up being way under the requirement. Let's see. And so there are range sensors and bumpers also for navigation. And I only had 50 days to get through it. I had, I didn't have a fixed budget, but it's my money, so I want to spend as little as possible. And next slide.
But there's an entry fee?
Yes, there was a $3,000 entry fee if you signed up in time, but by the time I even heard about the competition, that deadline had long passed. It was $5,000 to enter when I heard about it. So $5,000 entry fee, which was half the cost of the whole competition to me. Okay, so this is how this guy would function. It's been cannibalized. I managed to forget the digging arm in rushing over here today. So the actual excavating part of the excavator is missing. So there's a rotating disc with scoops on it, so I took that from the bucket wheel excavator design from the giant machine, the picture I showed earlier. That would go around, scoop up the dirt, drop it on a conveyor belt, which would bring it up. So the arm would be sticking off here with the wheel. They'd bring that up, drop it on here, and this is a box with a conveyor belt bottom. And as that fills up, there's sensors to detect the height of the regolith as it's piling up, and it would shift the conveyor belt so it could fully fill the box. And then it would know how full it was. And then there's a camera, which at one point was mounted up here, before being broken and bouncing around the cars from one side. So that's how it navigated to get over to the ramp. There are range sensors to detect the actual edge of the ramp, because it had to line up perfectly or else it would drive off the side or get one wheel up and get high centered. And also to detect the top of the ramp so it wouldn't just drive off and fall into the collective. And the robot didn't count towards the weight of the excavated regolith. That was the question that was asked at one point. And the arm would swing left or right, go up or down, and control all the conveyor belts. And so I wanted the robot just to park, and then the arm would keep excavating. It wouldn't have to drive around the holes that it just dug. Next slide. Okay, so there's my initial sketch, and then what it ended up looking like before. I mean, that was it, the day of the competition. So it was actually in one piece and working. It just doesn't look good. It just doesn't look like it now. Yeah. Next slide. Okay, so for the electronics, you know, it's just this is more of a slideshow for a few slides here. It's just or pictures. Block diagram, schematic, made the boards. Everything is just made in my garage. It's fun to go. Next slide. Okay, so for the navigation, this was tricky. It was a CMU cam, and the trickiest part about this was actually calibrating the system to work over any lighting conditions, because we didn't know what the lighting would be. All we knew is that the sandbox would be under a tent, and one side of the tent wouldn't be, there would only, so the three-sided tent. So we didn't know how light it would be. We didn't know if it was actually going to be shaded, because we didn't know what direction it would be pointing or what time of day, if it would be light coming onto the sand or not. So the picture on the bottom left is me taking a photo through the CMU cam in the shade, but you can see sunlight in the background where it's saturating the picture. It's all blue. And trying to find certain materials and colors that I could actually get to the camera to recognize over many different lighting conditions. That was a complicated part of this. And so on the bottom right, there's if it works, and it can actually identify the colors, it can pick out the center, the average position of all those colors, and figure out basically the center position of each of the two markers, which are just, for me, colors. And then it could project where I need to go, which is at the bottom of the ramp. And depending on the angle between, you know, the two different colors, you could figure out where you were in the ramp, and it had some reasonable idea of where it was.
So is your ramp two colors there?
Yeah, so that is a cardboard box that I just spray painted to test this on.
I'm sorry.
You can just leave it, it's fine. So yeah, the ramp was provided by the organization. My marker was just a board with two colors on it. And so I was looking for those two colors. And so if you're to the right of the ramp, you know, the top color will be more to the right than the bottom color.
So would you put the colors on the ramp?
Yeah, I had a board that just had orange cloth and blue cloth on it.
So you were allowed to provide your own ramp?
No.
I had a board that I put on top of the ramp that just had the two colors on it. The ramp was already there.
Okay.
My marker was just colored, just a piece of material that was colorful.
I see. So, and that was allowed in the rules to do that?
Yeah, we were allowed to have a marker within a certain area, and it counted towards our weight budget.
I see.
So mine was just, two colors. Okay, so the mechanical fabrication, lots of fun, just building stuff, welding, machining, putting it all together. That's just pictures. Next. Okay, so here is the software. Let's see, so this is the actual, on the left you can see the actual orientation of during the competition, where the rocks were placed and where the robot started. So I'm going to explain my software in that context. Let's see. So there were 4 states that I kind of condensed this down to, of the robot's kind of confidence in where it knew it was. And as it was approaching the ramp and becoming more aware of its position, if it got lost, it would tell itself it's confused, kind of back up and start over. And it was really fun to watch, because it would mess up, but it would always correct itself well, until the competition, of course, but it would get lost sometimes, and then it would go back a state. So I don't even know where I am, and then and I'll explain this better. So there's the 4 states where if it knew where it was at all, I think basically it's the bottom question is it facing the ramp? So if it wasn't facing the ramp, it really had no idea where it was. And so when it starts up, it was all these questions answers were no, and so it goes to the bottom routine, which is locate the ramp and point towards it. Next slide. Okay, so now the robot has figured out where the ramp is, turned around, it's pointing towards the ramp, or pointing towards where the bottom of the ramp should be.
What is the visual range of the robots to be able to do this?
I couldn't hear you. The visual.
Visual range at which the robot can tell where the ramp is.
I still can't hear you.
Visual range.
The range, the distance? It was, I knew the dimensions of the sandbox, so I was doing it basically from corner to corner. So it was 15 feet, something like that. Because I mean, it probably could do it further. I just didn't need to worry about that. Okay, so now it's pointing towards the ramp, and its next thing is to drive to the ramp. So in driving towards the ramp, it's driving there, and it's tracking the position of the ramp, and there's some coordinate transformation from the angle the camera is pointing to where the ramp is positioned within the camera's frame. So that will get it there, and then it can say, okay, I'm approximately 3 feet away, and know when to stop. Next slide. Okay, so now it's close to the ramp, and it needs to actually get right in front of the ramp so it can drive up it, and that's what I'm calling square to the ramp. So the way it did that is it would turn the camera to the side and try to keep the ramp on its right or left shoulder the entire time as it drives around until the blue and orange squares line up so it knows it's straight in front of it. Next slide. Okay, so it does that. It knows it's right in front of it. It turns towards the ramp, and okay, next slide. It approaches the ramp, which was actually fairly tricky because you've got to get the wheels to touch the ramp at the exact same time, or else it can kind of tip and not go right up it. And that was done with the range sensors that were pointing down. It would actually detect the change in range as you come up to the edge of the ramp. Next slide. Okay. So the last routine is a bunch of routines just stuck together. But there's no, it just runs right through them because now I'm in known territory once I'm at the ramp. There's no rocks on the ramp. There's no obstacles. Everything's known. So once it's at the ramp, goes up the ramp, it would dump out the dirt and then come back down. And then it goes into its routine of actually exploring around and finding where to dig. So it would do this kind of clockwise hemispherical exploration where it would wander out and detect if there's space to dig, and then it would dig. And if there wasn't, it would find somewhere else to go. But it always did this knowing where the ramp was. Next slide. And so it would just keep doing that, dig up a bunch of dirt.
Would it look at the ramp, or would it do it by odometry or something?
Let's see, so how would it explore?
Well, you position yourself on the ramp, and then you go out exploring and digging.
Yeah, so basically it's starting from the bottom of the ramp. That's its home base. It wants its back towards the ramp. So the camera's here looking at the ramp, and then it's going to turn left, drive away from the ramp a certain distance because you are in a sandbox, and it knew how far to go. And if it didn't hit anything, it knew, okay, there's clear space. It would come back up, turn around, and then dig. And then it would just keep doing that and exploring. If it bumped into something, it would back. It knew if there was room to back up and dig, it would do that. If there wasn't enough room, it would back up, point another angle, and go out again.
But you're saying it's always aware of where the ramp,
yeah, it's always, it knows where the ramp is. So the whole point is that it gets to the ramp, and once it knows that, that's its base. It just goes out from the ramp, digs if there's room. If not, it comes back and digs somewhere else.
It's always looking back at the ramp, knowing where it is relative to that.
Yeah, so the biggest challenge is getting to the ramp from the beginning.
Is the camera on a swivel, so it just keeps its eye on the ramp?
It's not actively tracking all the time. It's really only when I need it to.
And then it would just spin to find it, and then
honestly, I don't remember. It's been a long time. It was more complicated than just having the camera always look at the ramp, because there's lots of times where it's out of its view, you can't see it, and it doesn't have a wide angle lens. Next slide. Let's see. Okay. Let's show you a video of this thing. So this is basically, it walks through the development of this whole thing. Just mechanical development. This is where I'm integrating electronics and motors, just testing out its wheels, then testing out the arm that isn't here. So it had about 180 degrees of range. Testing out the digging with 1 or 2 scoops on there so far. Now here's the navigation part where it's interesting. So it's looking for the ramp right now. It has no idea where it is. And I had to stitch together a bunch of videos. So now it knows where the ramp is. It's pointing towards it. Okay, now it does. Now it's going to drive to the ramp. It's found the ramp. It realizes it's not directly in front of it, so it's squaring up to it. So it's going to drive around it until it's in front of it, so it could drive up it.
It's too wide for the ramp. Yeah.
Well, it's not actually going to drive over the box.
Oh,
it's just getting in front of it. And so for digging, there's lots of routines just for digging. I could talk about just digging for a long time. There's so many ranges of motion here, just degrees of freedom in like the depth and the resistance and the overcurrent of the motors and the conveyor belts getting jammed and having to back them up and unjam them.
So are you digging in that big of a pit of that sample material? Or
This is just a driveway right now that I'm tearing up.
Okay.
And it's some loose dirt that I found somewhere, took from some Caltrans guys. And so I was, moving it, and I'd have to shovel it back and then dig some more and shovel it back, and just to come up with all the routines. So it's going back and forth, and it's not. And no, this thing was never tested in regolith until the day of the competition.
Yeah.
50 days?
51 days.
Shit.
Were you doing this full time?
I did this, I started while I was finishing my last class, my master's degree, and then I did it just nights and weekends while working full time. And then the last 3 weeks I used all my vacation for the year and did this full time, yeah.
Was the regolith much harder to dig then?
The regolith, let's see, there is a video of it, it'll get to it, of actually digging in regolith. No, I don't know. Actually, it dug just once. I demoed it after the competition because it didn't. It got. I'll explain what happened in the competition.
Did you have a problem with navigation because you dug something that the?
No, it never actually dug in the competition.
Okay.
I don't think. No, one team actually did dig during the competition. I think. The rest of them all got hung up on navigation. So yeah, it digs for a while.
Did you do anything to protect any joints or the camera or anything like that?
To protect the camera?
Or joints from getting gunked up?
Not really, besides just using sealed bearings and doing what I could. Cross my fingers, maybe. So this is digging an actual regolith. It's just more cloudy material. I didn't have any telemetry on this robot, so it's hard to really know what's going on.
What's happened if in the slice of regolith there's something really hard? Do you have an emergency stop system?
There wasn't. So yes and no. In the sandbox, this was just regolith. There were no submerged rocks. There was nothing else besides the ground at some depth that we didn't really know what that was, but no one dug that deep anyways. It was monitoring its current in the motors at all times. So if it overcurrented, it would. Oh, it's me showing off my third place trophy. You can stop this. All right. Where was it? Yeah, there was current monitoring on all the motors. So if the actual digging wheel got stuck, or if it just was too deeply submerged, it would either stop the wheel or bring the arm back up, or there's all these different escape routes that I had in the software. So this is how it ended up. It ended up getting kind of high-centered on the corner of the ramp, and it's I was modifying the driving to the ramp routine hours before the competition. Don't ask me why, because it worked before, and I just thought I could make it better. And yeah, and so I was working on that, and I knew it was silly, but I had backed up all my code and put it in a folder, like, if it goes wrong, put me back in the code, or somewhere just labeled on my desktop. And worked on it for a few hours, improved what I wanted to improve, ended up causing problems elsewhere. Discovered that and said, okay, I'm going back to my backup code, and was so tired I couldn't find it, even though it was sitting right there in the desktop, the only folder. And yeah, so I couldn't find it, so I thought, okay, I'll just run it that way. And it did exactly what I told it to. It worked in the positions that I improved it on, and it didn't work in the two positions, or in the corner, which is the one that it wouldn't work in that circumstance, and that's where it happened to be starting. So it did a great job. It did just what I told it to do. Yeah, so it got stuck, and it was, once it got tipped up, it was looking around for the ramp, but it was kind of up on it and it couldn't see it. And it kept looking at this guy who had a red shirt. And I could see it staring at him and then trying to turn towards the guy. And the organizer's here, so well, whatever, I'll point myself out. But I told the guy to come over, I had a question for him. So maybe I could get him to turn the other way. And it was looking at him, but it still couldn't turn. Okay, next slide. All right, so that's the 2008 one. 2009 excavation challenge, or regolith excavation challenge. I think that NASA realized that the autonomy was just killing people, and they don't even have autonomous robots, so why are they telling us to do that? So they got rid of that requirement. So now it's the same challenge, just not autonomous. It's remotely controlled. There's limitations on that too that I'll talk about. It's the same setting, the sandbox, 4 randomly placed rocks. Now there is a known starting position for the robot. It's right in front. It's right where the ramp would be, but there's no ramp now. You can still have a beacon or a marker. So yeah, so now the robot starts where the ramp is, doesn't know where the rocks are, but there's a human in the loop. Next slide. Okay, so in the restrictions, there's no power limit now. It has to carry its own power source, and so they increased the weight requirement, 10 kilograms, to account for carrying a battery around. The footprint was now actually stated. You had to fit within a certain area of the sandbox. You know your starting position and orientation, you don't know the rocks, and okay, on the communications, there's so it's a human in the loop. There is a required minimum 2-second delay in each direction for communications, and 1 megabit per second bandwidth limitation. And the operator isn't just sitting here staring at the thing. He's somewhere else. He can only see what data is sent back. Okay, the same, no loophole competition or requirements, except now you can't store your own power, you have to. Next slide. Okay, so same trade spaces, except now, because there's no navigation, no autonomy requirement.
Question. You said no ordinance for people proposing to blow it up or something?
Well, it was in the requirements. I don't know what people were proposing, but if they didn't put that in there, somebody would have. And there were a lot of things where you'd think, okay, they didn't rule this out, and I know it's not what they want, and as long as I don't bring it up, I bet I could do it, but you wouldn't do it because as soon as they're aware of it, they tell you you can't do it. So there's a lot of things you have to kind of have to think, get inside NASA's head, or Matt's head. Okay, so let's see. Same trade space, except now the emphasis, I think it was really on the excavation method, because people are going to be in the loop if it gets stuck on a rock or if it gets lost, someone can correct it. So it's really going to be who can get the most regolith, not just who can get any regolith into the box. And so my design was really to figure out where can I eliminate any time that it wouldn't be excavating, and at the expense of complexity and everything else pretty much. And also just to make it as powerful as possible, which is, I guess, excavating as much as possible. So I have can you go to the next slide? Okay, so there's my concept. It would be continuously conveying dirt. So there's conveyor belts that would just, once this thing is in position and digging, the actual digging arm could articulate around. The robot would not have to drive ever again during the actual competition attempt. It would just continuously pull dirt up, dump it on the conveyor belt, dump it in the box. And so I'd spend a couple minutes deploying the thing, and then it would just run. And there would be no filling up a box, moving the, carrying it and then dumping it, which is what many of the teams ended up doing, which is a very simple approach and worked. Yeah, okay, so let's see. Cost a lot more money to build this one. I had more time. I had about 4 months. And then about the competition time, they postponed it a couple months because they added requirements, which I'll explain. Let's see, it's still 4-wheel drive, skid steer. It's really powerful. It's 2 kilowatts. I have a kilowatt-hour battery here that, since I'm only running for 30 minutes, I can run it's a 100 amp battery, and I'd be running about 70 amps continuously. So I decided to put pretty much all of my weight, or most of my weight, into the motors and the battery. So half of my weight are these two guys, which are the actual motors powering the digging, and then the battery. And then everything else is the other half. Next slide. Okay, so I don't have a picture for how it would actually be stowed, but this is how it would start. It would start in this position. There's a conveyor belt that mounts here. It's this guy, but if you look at it, it's kind of bent. It's because it flew out of a truck on the freeway a few months ago and got run over. So it doesn't work anymore.
Hazard on the moon.
Yeah. So that mounted here and it folded up and it held this thing in position because this is just free spinning. There's nothing really to hold it in place except for the conveyor belt. So the conveyor belt would fold up, hold this thing in place. So the conveyor belt's here, sticking up 9 feet, and then it would the excavator would start next to the collector box, and it would drive to the center. It would deploy the digging arm, and then the conveyor belt would deploy partially. The base would spin around. Am I doing this right? I'm getting something out of order here, but it's a complicated deploying scheme, but it worked in practice. And then, so once the actual digging arm drops down, there's these swing arms right here, which go up and down and they would control the depth to which you can dig. And so I'll demo this in a bit.
Were there still rocks and obstacles?
Yeah, there's still 4 rocks. So yeah, so but I can see where they are. So I would dig in between them, and then also the buckets would come up, and you could just drive right over the rocks, put the buckets back down. And it didn't have to worry about suspending the digging buckets or anything, because all the weight would rest on these wheels, and then for it to move around, it was actually driven out here on the outside. So there's no huge torque motors or anything in here that would take a lot of weight. It's just a little motor and wheels on the outside. Next slide.
Studded tires.
What's that?
Studded tires.
Yeah. Well, it keeps the rubber from spinning on the plastic rim and kind of helps. Okay, so from the concept to what it looked like, but you can see it. So next slide. Okay, electronics. This is my second set of electronics because I had the first set completely designed and then they changed the rules and that all went in the trash. So the new requirement was we had to use Wi-Fi and use their, not to knock you, Matt, sorry. So it was, implement your own 2 second delay and 1 megabit per second bandwidth limitation. And so everybody came up with their own way to do that. But if you weren't using Wi-Fi, when they then mandated that you use their transparent delay and bandwidth limiting system, which was based on, internet protocol, your system was worthless. It couldn't work. So I had to throw everything out and then basically now redesign the thing based on Wi-Fi. So this is the system. It's all off-the-shelf parts. Giant battery, netbook, 5 Robotech motor controllers. I don't know who made the servo driver, but there's plenty of companies to make those. Let's see. Some current monitors. There's a giant relay in here because, there's a rule that we had to have a fuse. There's no power limitation, but there's a rule that we had to use a certain fuse, which in effect limited the power, but they didn't specify exactly how to use the fuse. It was like I don't remember, a 15 amp fuse or some amperage that was kind of arbitrary, but I don't know. So it was in there. And they sort of said how you had to use it. They said if the fuse were to blow, the robot would be disabled. So you can run a milliamp through it to turn on a relay, which runs 100 amps through it, which is exactly what I did. So you take the fuses out and it's dead. You put the fuse in, it opens up the relay, it runs as much current as you want. And then all the rules. Okay, next slide.
I want to hear it.
Okay, so this is just some pictures of stuff that I made, mostly the tech shop. And the top right are these cool wheels I made, but then ended up not using because they were too small, sunk in too deep, and weren't really that great for regolith. They might have actually been okay in regolith. It's just I was testing in the sandbox at home that wasn't regolith, and they didn't work well there. And so I had to make a call at some point of, do I just hope they work in regolith, or do I make something that I know will work? So I ended up making these bigger wheels, which actually limit the range of motion of the actual digging arm. So I had to be real careful.
Home Depot doesn't carry regolith?
What's that?
Home Depot doesn't carry regolith?
No.
So how
No.
big is your sandbox at home?
I don't have one now, but it was a couple tons. It was maybe 8 feet by 8 feet.
I bet the cats in the neighborhood really.
Oh, I covered it. I made sure there were no cats in it. I didn't want to be playing that. Okay. Stuff that I built. Okay. Next slide. Okay. Here's the communication system that was specified. CSEWI is the organization that administered the competition. They ran it. And this is the cartoon they came up with to show us like how we're supposed to implement things. I'm not a network guy, so this is all gibberish to me. Luckily, I have a friend with NetCal Consulting in San Jose. They're great. He's my savior. He helps me make sense of this and get it all working. So, shout out to NetCal. Next slide. Okay, so pictures of this thing working. Is this thing blocking your view? Can you see that?
It's okay.
It is the subject.
That makes it look 3D.
It's turning towards the
It wants to eat cake.
Now I'm sitting in the hot flash.
Yeah, that's,
I
I
got
can
no
make
regular-
mind up.
Who's got the regolith?
Give me your regolith.
Feed himself.
I better have that recently.
Tonight's not gonna be a good night.
This is testing out the bigger wheels, making sure they actually work in my sandbox. And they did. That's it, them turning. Let's see.
Easily used.
Dig
1245.
But you're not cheap.
Reasonable.
Okay, so here's the smaller wheels that didn't work so well in the sand. They would just sink in and sand would just jam in there. That's painful for me to watch. I'm sorry, okay. Okay.
Do you have one where it gets arrested?
So for the actual competition, this is where it was set up, and that's where it sat for the entire length of the competition because we never got the link working. I tested on it the day before. It worked just fine. I controlled it fine. It actually worked. I had the thing there ready in time and done and tested on their network and it worked. And then the day of the competition, couldn't connect to the network.
Did you bring a video so you could show them that it worked?
I had posted videos online kind of to intimidate competitors. And stuff. There is a video of it actually demoing after the competition where I could just connect to it ad hoc and didn't have to use their network. Well, it's spliced together from many different angles. In the beginning's a little slow, it's just in driving, so let me skip this. So this is from the actual camera on the robot. This is my perspective watching it and operating it. So this is demoing after the competition. There was actually another excavator in the sandbox next to me. So this wasn't deploying the way I wanted to because there was another excavator I'd have to tear apart.
Excavator battle.
Yeah, so luckily my brother was in there and could kind of help it deploy. Because once the conveyor belt goes down, this thing's free spinning, and it couldn't deploy to the left where it normally would because there's excavators, so we had to spin it around, which is what it's doing right here. There's the other excavator. The guy who made this one's actually the first guy to have won NASA Centennial Challenge. It was the Astronaut Club Challenge guy.
How was his design different than yours?
His design was crazy. it was like a 40-gallon drum, or some big plastic drum thing that had an auger, like a snow blower thing, spinning in a circle, and it would just plunge a hole. And it really did a good job. It was amazing, and it just threw a bunch of aerials up in the air. But they had some kind of issue where I think they just didn't plug in their camera or something, and so they couldn't get any video when they started. So I'm moving it's deployed. I'm moving the digging arm over. I have to be careful about the ranges that I move it over because of the larger wheels I added. I don't have the full 270 degrees of digging room, so I have to put it down where I know, and I have to watch where the wheels are.
But you're at a remote location controlling it. You're not there right next to the sandbox, right?
Right now I am, because
okay.
this is after. I'm
right,
outside of the sandbox looking through, just operating.
But in the real competition,
yeah, I'd just be looking at the video. Yeah.
You had to be someplace else.
Yeah.
Okay.
Yeah. So I painted some of the buckets so I could actually have them as kind of tracers, because as it's going, I can't really tell how fast it's going, or put stickers and stuff on there just so I could see something going by. So they're running.
I was watching some of your videos on your website, and it looked like you were testing the conveyor here, and it looked like you started off slow, and then you went a little faster and a little faster and a little faster. What was the speed that you actually got it that you felt that it ran good and fast?
This is the fastest the buckets run. It ran better not at full speed, because the regolith is very different than the sand I played with. At full speed, it was just destroying the sandbox. And it was emptying that thing out. With the regolith, it would actually stick in the bucket a little bit longer and kind of throw it in a little, as it would dump here into the hopper, it would throw some of it out of the hopper because the regolith would come out slower. So there it's actually moving. So when I actually got it digging, let's see, had it kind of settled in at a good pace. It was they said it was about 1 kilogram a second. But that's, the high estimate there. And if you do the math and subtract a few minutes for deploying, that's better than Team 1. But he still won.
I was
so
going to say,
give it to him. He's
running,
great.
yeah.
I seriously think if it wasn't for the Wi-Fi, I would have placed, because the next two teams were great, but this thing would have dug way more than that. The team who won, it would have been real close, or he would have had it. And I think that's the end of this.
So what Wi-Fi do they have on the moon? We should figure this out.
Okay, I have a few more minutes. I'm going to show some more of these videos then.
Do you plan to compete again?
What's that?
Do you plan to compete again?
No.
Okay.
I won't. I was thinking about, they have other challenges now, but after talking to the organizers, so there's a nano satellite launch challenge. Yeah. And I've been looking into that, and after talking to the FAA and NASA and some people, it sounds like they don't know what they're doing at all, and it's going to come down to who can get the government to actually do anything, and it's not going to come down to who builds the best rocket. So I don't want no part of it. Not to be bitter. Okay.
Show the Osmo video.
Osmo? Okay, that's this thing. I was hoping if there was time in show and tell, I'd show off that guy. So, yeah, I guess I'll just show that one. Explain setting. Okay, so this is something I made for a competition at Cal Poly, San Luis Obispo, and it's basically it's like a ping pong table where you got to get all the balls from your side and throw them into the other guy's side, into a net on the other guy's side, and they're throwing it back at you. So this is it doing that.
It's like a lizard.
Yeah.
Whoa.
Is the banner to block?
So it won the competition, by the way. Yeah, the banner was to block, but there was an initial requirement that when it started, it had to be within a foot cube. So it was folded down, and then when it started, it popped up.
Is that autonomous? That's awesome.
Yeah.
Autonomous?
This, yeah. So there are a couple of good shots in this video where it actually shoots one, it bounces off the other guy and goes into my net and they get the point. And there's another one where it bounces off the rail and then hits the judge in the eye. You can't see it, but they comment on it, and there's photos elsewhere of him holding the eye.
So you coerced him into giving you the first prize.
Yeah.
Is this an internal how
It's open to, actually, they're starting this next year, it's open to anybody. So it's every April 20th, something like that, for their open house. And you win $1,000, you get first prize. So it's not $500,000, but it's $1,000, which is nice.
So where it's moving in circles like that, is that a requirement or is that?
No, so basically the balls are on these hoppers on each side. So there's 5 balls on each your left and right side, and once you've emptied all 5 out, they'll reload it up to some upper limit.
Would it know to wait if the other robot was like clearly in the way?
No.
That's why you got some bounce back. Okay.
Yeah.
Is awesome an acronym for something?
Awesome O is stolen from South Park. It's Cartman dressed up as a robot, called himself Awesome O. You know, it sounds like Awesome O, the Han robot.
Oh, I see. Oh, that's funny. See, there's a depth to that.
Is it just wall following there?
Yeah, it's just following the walls. It has switches on each side, and it has little wheels that go against the wall so it doesn't get stuck. It just cruises right along.
How does it know where the hopper is?
There's switches on either side too, so when it gets to the hopper, it detects that and stops. It's really just switches and whatever.
So it's not tracking the line, it's on.
No, that's too complicated. It's easier to find the wall. You can't miss the wall.
You're going to demo the big one?
Yeah, that is a really good point. Okay, this might take me a little while to put this all in, but I'm going to try to demo this.
Here it comes, Camp. It's going to ask you for some regular.
Yeah,
say yes.
got the regular.
And I'm not using the software I had for the competition or Wi-Fi or anything. I'm just going to kind of manually brute force this.
Where did you get your belt servos from?
These guys, motors, they're Allied Motion maybe. I could, if you want info, just ask me. They're gnarly motors.
NPC, okay, NPC. Oh, I mean, so
No, actually.
Where do you work?
okay.
Once you're at the peak launch on purpose, just keep it up.
What's that? Oh no, okay, so actually just I can move these freely, and I would have them in a position where I'm not actually like prepped to do a competition right now. So
Okay.
Get the carpet.
Engage these.
See, it's powerful.
Yeah, I'm not going to dig on my car. I don't intend to. All right.
Hey Sam, you might be on your
Watch your wheel there.
I think you might be interfering with your wheel.
Yeah. Oh, yeah.
There you go.
Let's see.
Whose linear action is that?
I don't remember who makes it. It might just be from Surplus Center, I think. It's not a real high quality thing. That'll probably be okay. I'll just run it up like this. Make sure everything's going to clear before I actually crank it.
This is like the evil Ferris wheel.
I can't really drive it because it has these fins on there that would make it very difficult to drive on hard ground. It drives fine in sand. I don't want to break it in here. Yes?
How do you keep the left chain phased with the right chain?
There is an axle right here that goes across.
Oh, it's a solid axle.
Yeah. So, and that's also, I have a rotary encoder on there too, so I can measure how quickly it's going. Yeah, so that's how I keep them in phase. What else? The conveyor belt. There's the shorter one right here. Actually, let's bring it over. As you can see, it's very straight and not smashed at all. So this thing mounts in here.
What's that display on the side? 0.6?
It's current, but something's weird about it, so it doesn't actually give me an accurate reading, but I've learned to recognize when it's 0.6 is fine. Yeah. Basically, if I turn it on and I see it go high, like if something's shorted and I've got a problem, but I've never had a problem with it. So linear actuator would mount here, but I borrowed it from a guy doing the Lunar Lander challenge, so I had to give it back. But this would mount in here, and then both these conveyors run, and it just this thing would rest on the actual the collector box, so it wouldn't have to support the weight of all that dirt on it, which would be a lot. So, and the only other degree of freedom in this thing is when this was actually all the way down, so if I did want to tear up the ground, it'd be resting on these wheels, so the buckets wouldn't actually pull it down into the ground. It's just resting there. And the reason I have it run in this direction is so if it does get caught, it would actually push back on the robot. It would kind of kick back, and which would make it easier for it to dig, so it would pull the buckets out. If it were going the other direction, it would just hog in and get caught. But it does make things a lot more complicated. The actual path for the chain to go through here, got tensioners just because everything needs to be able to deploy. I don't want the chain hanging on. And it took me a while to actually find a bucket design that could fit through this tight little area and still be large enough to carry a lot of dirt.
Got a real fast flip on the very end of it too, is it?
Yeah, it
doesn't throw the dirt in there.
No. Do I have more videos? Let's see. I thought I did. There's some on the hook. There's some online, but I don't have internet on this thing right now. So.
Yeah.
that's probably all we have time for anyways.
Well, do people have any further questions?
So where do you keep all your robots?
I have a garage right now. I keep them in.
Must be a big
No cars.
Yeah, there's no car in the garage. It's just robots and lathes.
There's a question over there.
Question? Yes.
The small wheels in front, would they be there on the actual moon, or would they just get for the test?
If any of this were going to the moon, it would be very different. This is meant for a sandbox. It's meant for winning the money, and that's it. Yeah, this would be ridiculous on the moon. Because
it would also have to be able to survive the launch from the.
This thing can't survive bouncing around in the van coming over here. Well, it has. I mean, it's here.
It's flying out of the freeway, of course.
Yeah, so I mean, it's held up except for being driven over on the freeway. But yeah, it's designed for the competition, not for space.
So what does NASA do with this information they get from this contest? Do they study all of the designs and
Sure. So I guess
Matt can take the floor.
So one of the things they did is they actually collected a database of all the different fault modes and challenges that they saw, so that basically when they're designing other excavation systems, they can sort of keep those in mind as things to kind of watch out for. And then what else? There's a number of lessons learned kind of things that basically have been collected from it.
any patent opportunities?
So the rules were set up where that was left as an option. The intellectual property stays with the competitor, and there's sort of a good faith thing that says competitors are willing to kind of talk to NASA if NASA wants to license something, but competitor owns the design.
Any more questions?
Well, thank you very much. Okay, that's sort of it for the meeting. So I just want to thank everybody for coming through this meeting and the other meetings earlier in the year. And we'll be holding our next meeting the last Wednesday of January. Don't ask me what day that is. I don't have a calendar in front of me. And at that meeting, I believe, okay, Patrick is going to, I believe, be showing us hands-on experience with the Will Garage robot operating system, okay, which is getting a lot of traction. So, you know, that's what's coming in January, unless things change. So again, thank you very much, and we'll see you next year.